In this video series, we're going to go ahead and learn about Self-Fields and Euler method, which is our first section in Unit 5. Our objectives today are to use initial conditions to find particular solutions of differential equations, use slope fields to approximate solutions of differential equations, and to use Euler's method to approximate solutions of differential equations. So we're going to start with general and particular solutions. Differential equations in x and y is an equation that involves x and y and the derivatives of y. For example, the equation 3x times y prime plus y equals 0. This equation has both x's, y's, and a derivative of y. A function y equals f of x is called a solution if you can replace all the y and y prime values with f and f prime and end with a true statement. Our general solutions usually contain a variable or a constant noted by the letter c, like this one, which says y equals c e to the x. In our first example, we are going to determine whether each function is a solution for the differential equation y double prime minus y equals 0. For letter A, we're going to find the derivative of y. So the derivative of sine would be cosine. Our equation says we need the second derivative, double prime. So to find the second derivative, we take the derivative again. The derivative of cosine is negative sine. Now we take our equation and we replace the values. Y double prime minus y equals 0. So y double prime is negative sine x minus y is sine x, and we're trying to show that this is equal to 0. Negative sine minus sine gives me negative 2 sine x, which is definitely not equal to 0. So for this first one, A, this is not a solution. B, y equals 4 e to the negative x. We want to go ahead and take the derivative, so y prime equals the derivative of 4e to the negative x. All you have to do is take the negative and put it in front. So the first derivative is negative 4e to the negative x. Remember, the derivative of e to the x is always just e to the x. The second derivative, y double prime, we're going to bring the negative down again. So negative times negative is 4, positive 4, e to the negative x. Again, we're going to use the equation that was given to us and we're going to test if it's true. Y double prime is 4e to the negative x minus our y value, which was 4e to the negative x equals 0. 4e to the negative x minus 4e to the negative x is 0, and 0 definitely equals 0. So we would say, yes, this one is a solution. Moving on to letter C. Y equals c e to the x. The derivative of c e to the x, c is just a number. It's a placeholder for a number. So the derivative of e to the x is just e to the x. So y prime is just going to be c e to the x. The second derivative is just the exact same thing, c e to the x. So now we're going to plug into our equation y double prime minus y equals 0. Y double prime is c e to the x minus y is c e to the x, and we're going to see if this is equal to 0. C e to the x minus c e to the x equals 0, and 0 definitely equals 0, So this one is also a yes. Go ahead and try the next few on your own. A particular solution of a differential equation is attained by using initial conditions to solve for the constant c, and then substituting back into the general solution. So let's look at an example of when we would find a particular solution. So we have a differential equation x times y prime minus 3y equals 0. We want to verify that c x to the third is a solution, and then we want to find the particular solution when y equals 2 and x equals negative 3. So let's start by verifying. So in this equation, x y prime minus 3y equals 0. So we need y prime. I know what y is. I need to know what y prime is. So the derivative of c x to the third will be 3c x to the 2. Now we're going to plug into our equation over here. X times y prime minus 3y. We're going to see, does this equal 0? Well, x times x squared gives me x cubed. And when I subtract these two, I certainly get 0. So we're good to continue because we have verified that this is a solution to the differential equation. Now we want to use our initial conditions where y is 2 and x equals negative 3 to get the actual particular solution. So what we do is we take our solution here that I've circled, this guy here, and we're going to plug in 2 to y, c, and then x is negative 3. So I get 2c times negative 27. Divide by negative 27, and we get that c equals negative 2 over 27. This is not my final answer. My final answer is we have to go ahead and plug that c back into our solution. So we're going to take our equation. Here's my last step. Y equals, and instead of c, we put negative 2 over 27, and then the x cubed. So we just replaced the c here with the c value we found. And there's the exact particular solution for this differential equation. Now you try a couple. Next, we're going to look at slope fields. A slope field is like a graph that has a bunch of tiny little segments on it that create, the little segments are like little slopes at each point. And to create a slope field, we have to kind of make a little table using the differential equation that gives us the slope. Because remember, a derivative is a slope. So if I give you a point, you should be able to tell me the slope at that point. A lot of words without work, right? So example 3a, we want to sketch a slope field. So it gives me 3 different points. So what I'm going to do is I'm going to go ahead and make a table here. This table is going to help me draw my slope field. I'm going to have one row for my x's. I'm going to have one row for my y. And then the last one's going to be my differential, which is y prime. So the first point we have is negative 1, 1. The second point we have is 0, 1. And the third point we're asked to plot is 1, 1. To find the y prime, we just plug it into our equation. So for this first one, our y prime is going to be equal to x minus y. That gives us negative 2. For the second one here, we're going to do x minus y, which gives us -1. And for our third one, we're going to do x minus y, which gives us 0. So the way we plot this slope field is we're going to plot these points. We have the point -1, 1, the point 0, 1, and the point 1, 1. And then we're going to draw a little line segment that kind of like pictures our slope. So a zero slope is this very right point over here. A zero slope is going to just be a horizontal flat line. A slope of -1 would be like up 1 over, up 1 over 1 this direction, right? So we can imagine a line that would look like this. We only want a little tiny piece of this slope, so we're just going to draw a little segment like this. For the slope here, we have -2. So if I were to draw this slope, we would go up 1, 2, and to the left 1. So you could see that our slope would follow this line. And we're only going to draw a little piece. So there it is. So if I take away my little scratch work here, there's my slope field. And it's not that noticeable, but you can tell that one of these, this one here, is a little bit steeper than this one. So all you have to do again, to sum it up, fill out your table, get that derivative, which tells us the slope for each point. And then you kind of just draw a little mark to notate where that slope would be. Now you try a couple tables. In this example, we're going to go ahead and try to match a slope field with a differential equation. So I'm given 3 equations and I have 3 pictures of the slope field here. So what we're going to do is we're going to go ahead and try to, I don't know, I'm kind of looking here and I see that all of these slopes are different at this point right here. And this point is the point, so what I'm going to use is I'm going to use the point 0, 1, and I'm going to test out each of these. So for 1, if I plugged in my numbers here, I would have 0 plus 1, which equals a slope of 1. Here, if I plug in 0, 1, this would give me just 0. If I plug in my x and my y to this equation, I just plug in the y, which is positive 1. So if I look at in terms of 0, 1, I see that this one has a 0 slope, which would be letter A. Now these two have the same slope, so now I got to pick a different point. Let's look at this point right here. That's the point 1, 0. So if I use the point 1, 0, we're going to do the same thing. X plus y, and we get 1. Over here, when I plug it in, there is no x, so I just plug in the y. So here, it should be 0. So the one that has a 0 slope is letter C. So that means that this graph, or this equation, matches letter C, and this graph, or equation, matches letter B. Now you try to match a few. To sketch a solution using a slope field, we're going to go ahead and I'm actually going to do this one on the calculator. So we're going to sketch a slope field for the differential equation y prime equals 2x plus y. So we just get our table the same way we did example 3, and then we plot all the points. However, your calculator can do this for you. So we're going to pull up the calculator to help us do this. So I want to graph, so I'm going to press the graph button. And then I'm drawing a slope field. So to do this, we're going to press Menu, Graph Entry, and we're using a differential equation. Our differential equation was the equation 2x plus, and then notice how this says y1, so I'm going to use y1. Because if I don't put the 1, it's not going to recognize that this and this go together. So we're going to use that as our equation. And then I have an initial condition of 1, comma 1. We go ahead and press enter, and it gives me my nice slope field with my approximation right here. Number 3 is using Euler's method to find a numerical approach for a particular solution. So when we use Euler's method, we're also going to make a table. Notice this right here, this little picture down here, it shows us what Euler's method does. You can see there's a little bit of error. I'm not going to ask you to find that error. I'm just going to ask you to find that approximation. So we use a small step that we call h, and here are the two formulas. For each x value, we're going to take the previous and add h. For each y value, we're going to take the previous and add h times the f of the initial conditions. So let's try this out. We're going to use Euler's method to approximate the particular solution of this differential equation, y prime equals x minus y, passing through the point 0, 1. So this gives me my x sub 0 and my y sub 0. And it tells me h is 0.1. So the first thing we want to do is we want to make ourselves a little table. And I kind of did this backwards. I put n on the bottom. Usually n goes on the top. So we're going to do many different steps. We're going to start with step 0, which is the initial condition. Sorry, our initial point. So let's do 0. Sorry, our initial condition is 0, 1. And I'm just going to do 5 because that's what I require you on your practice problem that I gave you on the next slide there. So to get our x value, all we're going to do is add this step of 0.1. So 0 plus 0.1 is 0.1. 0.1 plus 0.1 is 0.2. 0.2 plus 0.1 is 0.3. Then we get 0.4, and then we get 0.5. To get our y values, we're going to use the y formula. So if you remember, I wrote it, it was on the previous slide. We had y1 equals y sub 0 plus h times f of the initial conditions. So y sub 0 is 1 plus h is 0.1. And then f of x sub 0, that's this guy right here. X sub 0 was 0 minus y sub 0 is 1. And this gives me 0.9. To do the next one, y2, we use the previous. So we get y1, which was 0.9, plus h, 0.1, and then we're going to plug in our x1, y1. So x1 was 0.1 minus y1 was 0.9. We type that in and we get 0.82. Then we want to find y3. So y3, we take our y1, which was the previous, our h, our x from the previous, minus our y from the previous. We plug it into our calculator, and we get an answer. Then we do it again for 4, y sub 4. Our previous y value plus our h value times our previous x value minus the previous y value. Add them up and multiply, and you get 0.712. And the last one, y sub 5, previous y value plus 0.1, previous x value minus previous y value. And we get 0.681. Now you try.